Welcome back to the next video, everybody. Today we're going to continue trying to prove proposition 4. This is a hard one. We're going to go into part 4 of that, where we discuss the modules LH and LT. So let's get started. As of last video, we have an isomorphism T sigma. So this is kind of a reduced Hecke algebra with T sub m, where T is kind of a global full Hecke algebra, and M is a certain maximal ideal of T sub O, which is T sub Z tensored up to O, where O is our discrete valuation ring we've been working with this whole time, and where T sub Z is the subring of endomorphisms of S2 of gamma 0 of n generated by the Hecke operators, and where n equals n sub sigma was defined last video. I won't rehash that definition here. Please go watch that if you haven't. Okay, so we related reduced Hecke algebras to full Hecke algebras. So what we're going to do is for this n, we're going to let x be the modular curve x0 of n, and we're going to let j be its Jacobian j0 of n. And we're going to recall from chapter 3 that the homology group h1xz is equipped with a tz module structure, and that the Tate module TL of j tensored up to O over z sub L is isomorphic to the homology group h1xz tensored up to O, and that's equipped with a TO module structure. We can also regard cohomology H1XO, which is isomorphic to homomorphisms from homology to O, just by standard definitions, also as a TO module. And when we do so, the result is naturally isomorphic as TO modules to O homomorphisms from the Jacobian tensored up to O over Z sub L to O. Okay, so this is all known information already. So let's define this module Lsubt. So the Weil pairing, and I would encourage you to go back to chapter 3 if you don't recall the Weil pairing. This gives me a perfect pairing from the Tate module TLJ cross TLJ to ZL. And if W is that kinlaner involution W sub n of X, the modular curve, see chapter 3 on that kinlaner involution, you can consider the following composition. You can look at the map W star from TLJ to TLJ induced by W. So remember, this involution W from X to X induces a map between the Jacobian of X to the Jacobian X. That induces a map from Tate module to Tate module, which I'll call W lower star. So you can look at that map, and then you can follow it up with the map from TLJ, the natural map, from TLJ to homomorphisms over ZL from TLJ to ZL, the standard map there. Now, this is an isomorphism of TZL modules, okay? So what you can do is you can take this map here, you can tensor with O and localize at the maximal ideal M that we have from the first slide or from the last video if you like, to regard the module that I'll call Lsubt, which is TLJ tensored up to O over Z sub L, then localized at M, as a self-dual T sub sigma module of rank 2. And the reason you're allowed to do this is because of that isomorphism between T sub sigma and T sub M. Okay, so here is the first crucial module. It's Lsubt, it's self-dual. Self-dual was a terminology that was defined last video. So there's Lsubt. What's L sub H? So from here on out, we're going to let bracket sub T be the pairing obtained from our composition. Okay, so remember, this composition here is going to admit a pairing on Lsubt because it's a self-dual T sigma module. Okay. In a similar fashion, using W upper star, which is the induced map on duals rather than directly on the Tate modules, the cup product, which you can see chapter 4 to remind yourself of, and Poincare duality, we can regard L sub H, which is the name that we will give to the module H1 of XO localized at M, also as a self-dual T sub sigma module of rank 2. And we can give it a pairing X, a bracket sub H, defined by the image of X cup W star Y under the canonical isomorphism between H2XO and O. Again, for this, you can also see chapter 4. We also remark here that LH is canonically isomorphic to O homomorphisms from LT to O as T sub sigma modules. This is how I personally think of them. It's like you just defined L sub T, and then LH is just this. It's O maps out of LT. Okay. So here's the big theorem, which we will postpone the proof of until we are finished with the proof of the big proposition, the main proposition of the chapter, which is proposition 4. I'll call it Theorem TH. And it very simply says that the T sigma modules LT and LH are free. Okay, and this is quite difficult to show, so we'll wait to show it. But as a corollary, you get the following. If XY is a basis for the WP annihilator of L sub t, respectively the WP annihilator of L sub h. This WP guy was defined several videos ago, but in this chapter, okay. Then eta sub sigma, our congruence module relative to sigma, is generated actually by bracket xy sub t, respectively bracket xy sub h. So these pairings that we put on LT and L sub h, they actually kind of naturally generate congruence modules. Okay. The proof of this is easy. It's really just theorem TH and its proof, which we haven't gone through yet. Lemma eta to the d sub sigma, which is an old lemma from the beginning of the chapter. And then you can check that the pairings above are actually skew symmetric. That's really easy to do. And if you combine these three facts together, you get this immediately. Okay. So we're going to keep pushing forward further into the proof of proposition 4 in the next video. I'll see you then, and thanks for watching.